Okay, this is Chemistry 111, experiment number 7, determination of the acid ionization constant K sub A. Our purpose is to determine the pKa of a weak unknown acid. So you're given some mysterious acid. You're told it's a weak acid. You're told it's about 0.1 molar in concentration. And from that we're going to calculate we'll determine the pKa and calculate the Ka. Now, note that just because a substance may have a given concentration, that doesn't necessarily mean that it is weak or strong. The strength of an acid is determined by how much it dissociates. A strong acid dissociates completely. In other words, you're not an acid until you generate H+. So even though you might have hydrochloric acid, it's not until it breaks down into H+ and Cl- that it shows its strength. So the degree to which it dissociates is the degree to which it's strong. And we can measure that using a equilibrium constant, the acid equilibrium constant. And scientists decided to measure that by comparing the concentration of the dissociated stuff, that's where it's acidic, to the undissociated stuff. There should be a little closed brackets right there. And so by that measure, if you have a very strong acid, you'll have a very large amount of H+ because it'll be totally dissociated. That is reflected in these numbers here that you can see for Ka. See, hydrochloric acid, it's 1,000,000, so it's like very highly dissociated, essentially completely dissociated. Sulfuric acid, 1,000, very strong, very highly dissociated. But look at these numbers here. Oxalic acid is less than 1, as is acetic acid. It's down to 10 to the -5. Those are weak acids. They don't dissociate much. This isn't a matter of solubility. They solubilize fine, but they don't dissociate much. Now, because of this huge 11 order of magnitude sort of variation here, for better or for worse, scientists decided to go with a log-based system. And here's the corresponding log-based Ka, which we call the pKa. That's the negative log of the Ka. And that makes 1,000,000 turns into -6, and it makes the weak numbers get bigger. So we now have a backward system. The higher your number, the weaker your acid. Organic chemists like to quote the pKa of things that really aren't acids at all, like benzene and things like that. And they'll say, hey, it has a pKa of 30, meaning that it does not dissociate barely at all. On the other hand, when you go below 0, that thing is a strong acid and is strongly dissociated. So these are the two systems that people use, Ka and pKa. Now, an interesting thing that we'll take advantage of in this experiment is that we can very rapidly come up with the pKa by just finding the half the equivalence point volume. You find the volume it needs to neutralize this stuff. That's the equivalence volume. Take half of it, and bingo, you got your pKa. This is a result of some calculations that we don't need to go into in great detail. We'll jump right into this equation here, which is the Henderson-Hasselbach equation, which says the pK is the pH is the pKa as long as you can make this thing equal to 0. That means the log of 1 is 0. So when the A-, when the dissociated stuff is equal to the concentration of the undissociated stuff, then you have the pH equals the pKa. When is that? Well, halfway to the equivalence point. When you're at the equivalence point, it's all consumed. When you're halfway there, this value becomes 1. Log of 1 is 0, and the pH equals the pKa. So that's how we figure that out mathematically. In practice, you just get the equivalence point, divide that volume in half, like see right here. There's your volume. Divide it in half. Maybe it's, say, 25. No, this doesn't go from 0 to 25, but which is unfortunate, really. I mean, come on, it starts at 23. Take that value, divide it in half, and find the pH at the half equivalence point, and that's your pKa. If you need to go back, and you will, this is an important little tip for this experiment. When you have the pKa and you want to get the Ka, just take 10 to the negative pKa and you got it. In other words, 10 to the 6th is 1,000,000, so it should check out. Now we're going to go ahead and perform our titration. We are going to tell you that that weak acid is about 0.1 molar. So we'll titrate it with 25 mils of 0.1 molar sodium hydroxide, meaning that maybe we shouldn't go through our burette before we do that. Let's go back here. Okay, fine. All right, here's our procedure. First, record your unknown number. Condition your burette means rinse it with the same stuff you're going to titrate it with. So we'll run sodium hydroxide through it once or twice, and then get 25 mils of your unknown and measure that volume precisely. That means to the 100th of a mil. And then standardize your pH meter as instructed using Logger Pro. There are some long, ugly-looking instructions that you need to follow to make sure that your pH meter is standardized, and I am not, as usual, going to list all those weird Logger Pro instructions. Fine. All right, stick a pH probe in this thing and stir it magnetically and record that initial pH. And then begin your titration. Drip in about ½ mil increments and follow the instructions. I think it says press keep every ½ mils. And then once the pH starts to just drastically change, we're not using an indicator here. We're just looking for this sudden rapid change in pH, and it should be very, very obvious. Switch to smaller increments. Just give it a little squirt. Maybe it'll be about 1/10 of a mil. I don't know. Now, to make sure that you're doing things properly, go 2 mils beyond the equivalence point, all the way up to pH 11 or so, and then you're done with all the wet work. The only thing that remains is clean up and do the data manipulation. Now, we'd like to get the half equivalence point, so we like to calculate this number as precisely as possible. But this inflection point where it changes from this kind of a curve to that kind of curve might not be easy to estimate just from a titration plot. So we're going to do a little math to make it more precise. Look at how precise it gets when you take a first derivative, whammo. That makes things much better. So the power of math is evident. And I'm told that the second derivative is even easier to determine, where that value right there at the x-axis is your equivalence point. Don't forget to get the pKa. You need half of that. Handy notes. Read your burettes to 100th of a mil, not 1/10. Use the 400 mil beaker for rinse waste, and 150 mil beaker for the titration, and the 100 mils is for your sodium hydroxide. As said before, titrate in your ½ mil increments. Go smaller near the equivalence points. It's very easy to lose the stir bars when you pour things down the sink, so take the thing out first. You can use a stir bar retriever to do that if you want. And we're not going to just write down all this data in your lab notebook. We're going to make life easy for you and just print all the data tables and these 3 graphs and add them to your report. It may be actually these 2. I'm not sure whether it's 2 or 3. Just follow the instructions and do what it says. You don't have to enter any data tables in the lab notebook this time. We only have one calculation this time, and that is the Ka from the pKa. Take note of this part right here and make sure that it works when you try it for a few sample calculations. Here's the results that you need to report. Your unknown number. The equivalence point volume that you've gotten very precisely either this way or even better this way. The half equivalence point volume, I think you know how to do that. Take half of it. And then corresponding pKa is the pH at the half equivalence point. And then do the calculation for the Ka, as we've said before. And here's a weird note that was added just recently that I'm just going to read verbatim and try to make some sense out of it. After printing out the graph, go to the graph options, deselect the D1 and D2 curves. This is in Logger Pro, so they don't show up on the graph anymore. The reason for this is because that'll show the original pH plot expanded to a more accurate scale. So probably the scaling's off and that fixes it. Use this to place the cursor over the plot at the equivalence point to read off the pH for the Y value. This value is the pKa. Now make sure that makes sense. I'm a little worried that it sounds like you are at the equivalence point, not half the equivalence point. So be sure that you can make sense of that and everything works out well. Okay, this is experiment number 7, determination of the acid ionization constant.